I welcome everyone to the weekly review. We're going to go ahead and get started going through these problems here that we prepared for you. So this first one, and I'll ask questions if you guys don't want to answer, you don't have to. This first one, can anyone tell me what type of reaction it would be?
So the iodines are tertiary, I believe, so 3 degree, and then the nucleophile, so I think it should be SN1.
Yes. Does that make sense to everyone why it's SN1?
Yes.
Yes, we have a strong nucleophile, not a good base, right? So we're ruling out E2, and it's tertiary. So it's going to be SN1. So let's go ahead and draw the SN1 product here. Right, and that happened because this iodine is just going to spontaneously leave. We're going to get a tertiary carbocation there, and then the sulfur is going to attack. All right, let's move on to the next one. This one. So what is our substrate here? What is it? Primary, secondary, tertiary?
Tertiary.
It's tertiary as well. Tertiary. It has a good leaving group, right? So iodine. However, what is this? Is this a strong nucleophile, strong base, weak nucleophile, weak base?
So whenever N is attached to it, it means it's a good.
Yes, strong. It's strong, not necessarily strong base, but in this case, yes. So that's plus, and this will be minus. So OCH3 is a strong nucleophile. However, it's also a strong base. And because of that, this being tertiary, what reaction mechanism type does that give us?
Again, SN1?
Could be, but more likely E2.
Okay, so in our defense, did you get to E2 in Professor Thompson's class?
Yeah.
Okay, because.
On your quiz this week, they're going to tell you what it's going to be as well.
Yeah.
So don't worry too much about that. I'm just kind of preparing you for the exam. But yeah, if you don't want to answer that, I'll tell you what it is and we'll do that because that's what you'll be expecting on the quiz. We're just going to go a little more in depth than that. So this will be E2. Right? Now, one of the conditions for E2 is that there must be an anti-coplanar hydrogen, and there is one here, we just don't have it drawn. There's also some here. So the question is, should I eliminate on one of these hydrogens here and get this, or should I eliminate this hydrogen and make that?
The second one?
The second one, this one, will be the major product. You will still get some of this. This is the Hofmann product, but the Zaitsev product is going to be the major product because of this alkene here. It's more substituted. And we have a strong, small base. Does that make sense to everyone?
So whenever it can be either base, strong base or nucleophile, so we have to look for the E2.
Yeah, look at the substrate and look at the base. Yeah, generally, it's going to be on that table, I believe. It'll have a list of the strong nucleophiles and strong bases.
Mm-hmm.
When you say more substituted, can you explain to me what you mean?
Yes, so I'll do this one in red here. So this alkene here, this guy, is one substitute, twice substituted. So this one would be a secondary alkene because there's one methyl group coming off of it and two. So I'm going to draw that over here. So this alkene right here, where there's a carbon here, a hydrogen here, this one is unsubstituted. This alkene that I'm going to draw here, we will make this guy monosubstituted. So there's this carbon here, right? And this inline structure would look like this. So this guy here makes it monosubstituted. This would be disubstituted.
Okay.
And the last two, this is trisubstituted, and this has been substituted 4 times. So these are more stable.
Okay.
So there is this. So since this one here is 1, 2, 3, that one is substituted 3 times, this one is only substituted twice. So we're going to take the most substituted one as the Zaitsev product. So that'll be the major product, and this is what you would answer on the quiz or test. Alrighty, moving on. So this one. So in this case, we have this weird looking thing, right?
can be no, it cannot be a trans because they both are not true.
So this is a strong nuke, strong base. Strong. And it's a bulky base, right? It looks like this. So you need to be familiar with this, or it also looks like this. So this will be minus, this will be plus. And sometimes they like to show it like that. So it's got this giant parachute looking tail on it that's going to make it bulky, and bulky bases are generally going to do E2. They can do other things, but generally E2. So I'm going to erase it down here. I guess I can leave that drawn. This one's going to be E2, so I'll tell you that right now. Now, one of the conditions for E2 that we mentioned earlier is it needs to be an anti-coplanar hydrogen. Now that translates to on the ring, the hydrogen must be on, if this is on a wedge, the hydrogen needs to be on a dash. And bulky bases also prefer the Hofmann product. So if we were using this reagent in the previous example here, we would have chosen this to be our major product. And the reason for that is, since this thing has a giant parachute, it has a hard time getting to the most substituted hydrogen just because of sterics. So there's all these other methyl groups around the place that prevent it from going there. So it prefers to grab any hydrogen it can, and that's why you prefer the Hofmann for bulky bases. Now, in this case, do we have any anti-coplanar hydrogens, and if so, where are they? Do I have any on this carbon here?
Yes. So it should be a dash. This part?
Yes, but if you look here, this methyl group here, I know it's not drawn very well on the picture, but it is a dash.
Oh, it's a dash.
That is a dash, and that's a
It should
methyl.
be a wedge then.
So in this case, the hydrogen is not drawn, but we know it's on a wedge. And since the bromine's on a wedge and the hydrogen's on a wedge, we cannot take this guy because it has to be anti-coplanar for E2 to occur. The other thing we know is that we don't actually want the Zaitsev product. We want the Hofmann product, but we only have one other option, right? And that's this guy here. There is a hydrogen here, right? There's also one on a wedge. So we're going to take this guy off and eliminate there. So let's go ahead and draw the product. On there. And then this carbon is still on a dash because we didn't affect anything there. So it's still going to be have its stereochemistry. So does that make sense? And as we can see, even if we were able to eliminate on this other one, we would have still preferred this because it's a bulky base. So even if this were on a wedge here, we would have still gone for this one due to this. So there was kind of a double chance here to kind of hinting to take the other hydrogen off. Okay. Any questions over this guy? All right, so moving on. This one is actually kind of tricky, probably one of the harder reactions in here. So let's go ahead and go through that. So does anyone know what this first thing does? It's called a tosylate, and it's going to be a protecting group. So I'm going to draw it out because they can also show it to you on the quiz in this format, and you need to be able to recognize it.
So we do that whenever there is like O wedge attached to them.
Yeah. So this is what it looks like here, and I will go through the mechanism. You won't have to go, but I think it makes it a little bit more clear. So here is our this guy I'm drawing. So the OH is going to attack the sulfur, and the chlorine is going to get kicked out. So we just bonded our oxygen directly to the sulfur. I'll actually go ahead and show that in red here, just so we can see the bonds a little more clearly. So that's these lone pair, and they're forming a bond here. So let's redraw it. So we have the oxygen here. Now I'm going to skip a couple steps and get rid of that hydrogen because we don't really care, we just kind of want to see what it looks like. So we have this oxygen bonded to the sulfur. The chlorine left, and our benzene ring is still here. Now this circle inside the benzene ring, we can draw that, or we can draw it this way. They mean the same thing. So that's what we have now. right? And now I'm going to tell you, because this one's hard to know, this one's going to be SN1, since you'll be told on your quiz. This is SN1. So in an SN1 reaction, what happens first?
Cation.
So the leaving group's going to leave. So now this whole thing here is a good leaving group, right? Because it's extensively resonance stabilized. So what's going to happen, this bond's going to break and it's going to leave. And we're going to form our secondary carbocation here. And this left, and this is just so we can see why it's such a good leaving group. So this has a minus charge with its lone pairs I'll draw. And now this, it can resonate a lot of times, right? So it's a very good leaving group. So that's that. And now we have a secondary carbocation. But what is this position right here?
Just tertiary.
So what's going to happen?
It's gonna do the shift.
Yes. So what type? Hydride or a methyl?
First you always start the hydride.
You got it, yeah. Hydride shift. So we're going to move a hydrogen because that's easier. So let's move the hydrogen. And by easier, I mean it's more favorable because it's a smaller thing to move. So let's go ahead and move that. So we have this hydrogen here, and it's going to shift over, and we can denote that as H squiggle. So now that hydrogen went here, and the plus charge, or carbocation, is now tertiary, so it's much happier. Now, in the second step, drawing your attention back over here, we have CH3CH2OH, so I'm going to draw that over here. This guy. And now what is it going to do?
It's gonna attack the cation.
Exactly, it's going to attack the carbocation. So we're going to get that, and that would be the final answer to this guy. All right. Any questions on that one? Just on a side note, if I was wondering, the AgNO2 is just supposed to help clue you into an SN1. It doesn't really have any relevance in this case, other than possibly stabilizing the carbocation with the NO3 minus, helping stabilize the
It
plus
helps
charge.
with the ionization, right?
Yes, exactly. Yeah, because it's going to stabilize the carbocation. It can line up right here and help stabilize that transition to the hydride shift. But it's not super relevant. Even if they gave you the first two steps, you'd probably be able to do this one. All right. So this one, so this here goes to this, sort of. Oh, weird. I'm going to erase some of this here. It's okay, just because I want to keep it a little bit cleaner. So erase that. And I'll redraw it for everyone. So we have that. That's our final answer to that one. So let's do this one. So in this one, I think drawing the mechanisms helps because once you've drawn them enough times, it just becomes a little bit clearer. So let's do this one. I'm going to draw this one because I think it's a really important one to know to see at least one time. So
So it's 1 degree and it's attached to OH.
so what type of reaction is this going to be?
E, it would be elimination.
Well,
No.
it can't really, because this is protic, right? It's not a strong base,
Oh.
it's a weak nucleophile, weak base.
So for E1 it doesn't matter, right? Or no, base is important.
Yeah. So we're not going to do, I don't think we do E1 in any of these today. I am going to give this one to you. And on this one, you'd probably be given what you have up here, this AgNO3, would generally be given with this problem as well.
So
On
it
a
would be
quiz.
SN1.
It would be SN1 exactly. So the first step, like we said, is going to be the carbocation formation, right?
So can we still do SN1 for if something is like a primary?
Generally no, but I'm thinking this AgNO3 was actually meant to be written down here with this one, because it wasn't needed for the first one. But if you were told to do SN1, in which case the key says to do SN1 on this, we'll go through. So generally no, you're right, it would be SN2. So doing SN1 on this, we get this carbocation, and now this is a primary carbocation next to a tertiary position. So what is going to happen here?
Shift.
Yes. So the question is it going to be a hydride shift or a methyl shift?
Should be metal shift.
Yes. Yeah. So we're going to go ahead and do both the products because we'll see which one we like better. So if we do the hydride shift, the hydrogen's going to shift over here. So this is doing the hydride shift. We get this, right? And then the CH3OH can attack it. And we get that. Now, the other thing we can do is a methyl shift. And this is one that confuses a lot of people, so I'm going to erase some of this just to make it clear. So I'm not going to go, I'm going to erase that. So we have, yet again, primary and tertiary here. So what can happen is this methyl can actually shift over and we can undergo a ring expansion since it's a 5-membered ring. So the way I like to draw that is to visualize it this way. So we're breaking this bond here. So I'm going to go ahead and break that with my eraser, right? And we are rebonding it to this guy. So I'm going to draw that. And this is kind of confusing if you look at it in one step. But so we bonded to this carbon, which means the carbocation moved. Now, we formed a bond here and broke a bond and didn't reform one here. So the carbocation is going to shift here. Now, as you can see, we have a 6-membered ring. It's just drawn in an ugly way, right? So I'm going to go ahead and redraw that. Now, the thing with this one is it is still secondary, right? So it's still a secondary carbocation. However, we have rearranged the ring and relieved some of the ring strain that occurs in 5-membered rings. So now we have HL, CH3, and that will attack, and then we'll get this. So you can argue for either one of these, because in this case we still have the ring strain, but we have a tertiary carbocation. In this one, we lost the ring strain, but we still have a secondary carbocation, which is still better than primary, but the carbocation is not as stable. So either one of these would work for this question. But generally on the test, you'll see ring expansion. So if you see one that is a ring expansion, I would probably go with this one. In this case, you could argue either one, but a lot of the times they like to add a methyl group to make it so the ring expansion is also tertiary. Any questions on that? All right. So this one, what about this guy? Let's say we did SN1 on this one.
The cation shouldn't move because it's already attacked.
Let's try. Let's see. So the leaving group leaves. We get a positive charge here.
So the positive charge is on a secondary
Exactly.
and it's next to a tertiary. So it will move.
So we're going to move this hydrogen that's not drawn over. Positive charge there. Then the O can attack, as we've shown many times before. And we can go straight to the product here. Is there any questions on that one? So a lot of methyl shifts here going up, right? So now on this one, I'm going to tell you what it is, but before I do, does anyone want to try and guess what this reaction is going to be here? I guess I'm going to draw it.
Is it SN2?
This one's going to be E2. It's secondary. So generally, secondary is going to undergo SN2 or E2. But in this case, it's next to this tertiary or quaternary carbon, and they call those neopentyl groups. It's similar to a neopentyl, and those do not do SN2 because of steric hindrance. So this one is going to do E2, and we know that because this is a strong nuke and a strong base, right? It's not protonated. So doing E2 here, there's no carbocation intermediates because remember, it's a concerted reaction. So let's go ahead and do this one. So where am I going to eliminate? I'll let you guys kind of try that one. Don't be afraid. If you can't do it, we're going to go through it. So
iodine goes, and then by the bulky, then from there, shift.
So remember, E2 are concerted, so there's no carbocations, so there's no rearrangements in E2 mechanisms. So there are no hydrogens here, right? This carbon is bonded to 1, 2, 3 other carbons, this one being the fourth carbon. We need a hydrogen adjacent to the leaving group, and this is our leaving group here. So we're going to have to take one of these hydrogens here. So let's go ahead and take one of those off. And since we do that, it's an elimination, so we're forming an alkene. So we get this. Any questions on that?
The hydrogen iodine, they left, and that's what it formed the double.
Yes, it didn't leave on its own. This base came and grabbed it, causing this to fall into a pi bond and kick out behind that. So this one, let's do this guy. So I'll tell you again what it is, but what is this reagent? Strong nuke, strong base, weak nuke, weak base. It is strong, yeah, because we have an A plus and H minus, which is interesting, right? It's called hydride. So we have a hydride, and that is a strong nuke and a strong base. It's actually one of the strongest bases out there. So since we have a strong base and this tertiary leaving group here, right?
It will be an elimination.
It will be elimination, and in this case, it will be an E2 reaction. Now, because no stereochemistry is shown on anything but that chlorine, we can assume here that there is hydrogen here. Now, if there were wedges and dashes, then we need to check. And one of the ways we could check is to actually go ahead and draw the chair conformation. But I'm not going to do that for this one, just because I know it can be here because they didn't show it. They showed it on a line. Now, if this hydrogen was on a wedge, then we couldn't eliminate it. Not with this mechanism. So let's do that. So I know it can be on a dash, and since it can be on a dash, we say it is on a dash. Now, this is also going to do an elimination. Now, it could take this one, right? But it could also take one of the ones here. Or one of the ones here. So which one are we going to take?
So this one.
This one?
Yeah.
This one. Well, that would make our alkene here,
Uh,
and that would be 1,
1,
2, 3. Try substitute. If we took this one here,
would be 1, 2, and then
3 as well.
So the other one was making 2.
So this one here, if I eliminate this hydrogen, I'll get the alkene here. And in that case, it's 1,
1, 2, 3,
4. So that one's
yes.
4. And that one will be the best, the most stable, exactly. So we're going to go ahead and take that hydrogen there. And we are going to get that. Now just be aware, sometimes they like to draw these lines here on one of these rings on a wedge or a dash. And sometimes you need to check to see if that hydrogen can be anticoplanar, so which means this would have to be axial since it's on a ring. Any questions on that?
what you said?
Yes. So I'll go ahead and draw a ring. This is a separate question. So this is the cyclohexane chair conformation.
Mm-hmm.
So if the chlorine is equatorial, there's nothing that can be anti-coplanar to it. So the chlorine has to go axial, so the chair has to flip. Now I'm just going to redraw it here. I'm not going to actually do the chair flip. I'm going to say the chlorine's axial in this case. When the chlorine's axial here, looking into this carbon from this, if we were to draw the Newman projection, we would see that this hydrogen is axial as well, and that means they're anti-coplanar. So we're looking right down there. So that's just a side note. I wouldn't worry about it too much, but it is a possibility. So with that, moving on. We are almost through this thing. So let's go ahead and rank these alkyl halides by SN1 reactivity. What determines the reactivity for SN1?
So it's third degree, second degree, and
Mhm.
first.
So it is the ability of the leaving group to leave.
Yes.
So we have our rate law, and you will want to know this for the test. I don't know if you'll need to know it for your quiz. Rate equals K substrate. And the substrate is this guy here, right? The one with the leaving group. So we can see that in our rate law here, the rate is proportional to the rate constant times the concentration of the substrate. So the type of substrate is going to matter here. Like, just like you were saying, tertiary would be better than secondary.
Mm-hmm.
There is one thing better than tertiary, though, and that's
the
allelic
that
or resonance
is-
stabilized. Yes. So the more resonance stabilized, the more ability there is going to be for the carbocation to form, because the carbocation will be more stable. So let's look at these. So if this chlorine were to leave, I'm going to draw all the carbocations right above the molecule here. If this chlorine were to just up and leave, you get a secondary carbocation, right?
Mhm.
On this one, if this bromine were to leave, you get a primary carbocation. If this iodine were to leave, you get a secondary resonance stabilized carbocation, right? So we know that one's looking really nice right now.
Yeah, so it should be one without the resonance, like it should be in the top ones.
Yes, yeah. I'm gonna go ahead and finish them before I rank them, but yes, you have it right there. So on this one, we have secondary as well. And now we have two secondaries, so there's something else we're gonna need to look at next. And I'm gonna
Trend.
kind of, we'll see. We'll come back to that in a second. And then this one is also going to be secondary, right? So I didn't draw the plus here. So this one can be a little bit tricky. So let's rank the worst one first. So which one of these up here, so we'll say this is secondary as well.
So the primary.
So this would be the worst one, and thus would be 5. Right? Now, the question is, of these, what's the best?
The resonance.
This would be number 1, because it's secondary and resonance stabilized. Well, you may be saying, but look up here, you have a secondary carbocation, but it's next to this tertiary position, and this tertiary position that it can rearrange to is also allelic, right? It is resonance stabilized if it were to rearrange. However, you're correct in stating that this is more reactive because this carbocation forms immediately, whereas rearrangements take time to occur. So because this rearrangement would take time, this Alrighty. So the following structure undergoes sobolysis with methanol. Draw the mechanism, energy diagram, and major product.
So it would be SN1?
Yes. So it's tertiary resonance stabilized. So methanol, anyone tell me what that looks like?
Yes.
Yeah.
Methanol?
Mhm.
So it would be CH3OH?
So CH3, OH, methanol. So we're doing SN1 on this, and it asks to draw the mechanism here. So we'll go ahead and draw the whole mechanism for this reaction. So what's going to happen, this chlorine is going to leave, right? And when the chlorine leaves, so I'm going to draw the arrow down here, just showing that we're moving through this thing. We get a tertiary resonance stabilized carbocation. Now, and sobolysis also means SN1, just if you were wondering. We have the methanol. Now the methanol is going to attack the carbocation, right? And it's not going to attack the carbocation over here, because the carbocation is going to exist more of the time on the tertiary position. And we drew an arrow from the oxygen to the carbon, so we're forming a bond between those two. So let's redraw this. So we have the oxygen here, carbon here, and the hydrogen's still there because it wants the complete mechanism. We'll go ahead and show that this guy has a lone pair. So that oxygen has a positive formal charge here. Well, there are more than one of these methanol molecules floating around in the solution. So another one that's just hanging out in the beaker can come along and act as a base. Take this hydrogen and these electrons in this bond here and collapse back onto the oxygen. Giving us our final product. So this is the one we care about. This is the product. But this over here, just to show what it looks like now, would have H2O positive charge CH3. So this is the guy we care about, and that is also our finished product.
So those two are intermediates?
So yeah, this would be an intermediate. Yes, this would be an intermediate as well. This is the main intermediate. If they ask you to draw a diagram, this is the one you draw.
Okay.
Because we're looking at the product, it's intermediate. Any questions over the mechanism? Okay. So let's go with this. So I am going to, can I erase this? Okay. So I'm going to go ahead and erase this so we can draw the energy diagram. So this here would answer the question for the major product. This thing we showed here answers the mechanism. So on your quiz, you obviously wouldn't erase this, but let's redraw and draw the energy diagram. So we have, here's our energy diagrams. This is going to be E. And then on the x-axis, we have reaction coordinate. So because this is an SM1, it's going to have two humps, right? So we're going to have the first one where the chlorine, this is the chlorine leaving here. That's what's happening. So we have some energy in our molecule, and it's going to a transition state, right? One hump, and then a valley. Now, in this case, the chlorine's left, and this is our intermediate here. And I'm going to go back and label this. I'm just going to talk through it. And then as the bond between the methanol is forming, we have our next transition state, which is lower in energy state than this one. So I'm going to draw it a little bit lower here. And then going to products, and we're going to assume this is an exothermic reaction. So this would be the reactants. I'm going to label that as R. This will be the first transition state, which we denote as this double dagger, transition state 1. This will be the intermediate. I'm going to denote that as an I for intermediate. This is the transition state number 2. And then this will be the product. And one of the quick ways you can remember is RIP, RIP, or reaction intermediate product. So the reactant is this guy before it reacts. The intermediate, I'll draw it right above it. Tiny. Is the carbocation. And then this transition state is when that bond is forming. I guess I'll try and draw it. I don't think they care if you draw it. So you have the bond here. I've dashed it between the CH.
For transition, we don't have to draw, right?
I've seen them ask it on some old tests, but not often. So it'd be this, and you're saying that this is the delta plus here, delta minus there. So that would be the transition state. And then the product is what we drew with everything finalized. So let's see, I think that answers the question. Oh, there's some more stuff we need to know. So the energy of activation. The energy of activation is going to be between the reactant and the transition state, the first one. So it would be the difference, I'll draw the middle here, in the height here. So this would be the energy of activation here. And then they denote it as delta G. In this case, they're denoting the enthalpy instead of the Gibbs free energy here. So the difference between the product and the reactant here is going to be the amount of heat it gave off, and they're calling this delta H. I've also seen it denoted as Gibbs free energy.
Yeah, delta G.
But on the key for this one, they had it as delta H as well. So that would be that. Now, on a side note here, the hump that is larger on our reaction graph, so this hump's here, right about there. And then this one's a little bit higher, right? So the highest hump is the rate determining step, the rate limiting step. And this is kind of how we know that the leaving group leaving determines the rate law, right? Because we said it only depends on the ability of the chlorine to leave. Because if we don't form any intermediate, it doesn't matter how much methanol you add, this step will never occur because we have to get over this hump first. And for this hump to occur, the chlorine must leave. So the higher the hump, the tallest hump is the rate determining step, also known as the slow step. Moving on to the last thing. Now, there are multiple answers to this, and it does depend on your professor a bit here, but the important thing is the why you're saying it. So this is an SN1 reaction, so I always like to start out by stating the rate law. So rate for SN1 equals K substrate. They just normally write it sub. I wrote substrate earlier, but I'll just write substrate. So rate equals K substrate. So right there, we can see, unlike SN2, our nucleophile is not in the rate law. So they're saying if we changed methanol to methoxide, what would happen? So we're going from, I'll draw it here. We're going from this, and methoxide is just the deprotonated form of methanol. So now we have a minus charge instead of a proton. So we made a weak nucleophile into a strong nucleophile. So what do you think that's going to do to the rate?
For SN1, we do weak nucleophile. So
But you can also use a strong nucleophile. Either one will work, right?
Yeah.
But what's it going to do to the rate of the
gonna
reaction?
A little bit decrease it because it's going towards weak.
It's not going to change. And how do we know that? Well, we said it doesn't matter how fast this second step occurs here, right? This one had an H. If this was a minus, it would be more ready to attack. But in our rate law, the rate of the reaction is only dependent on the rate constant and the substrate concentration and type of substrate. So changing the nucleophile here doesn't affect our rate law. So this one won't do anything. So we'll say nothing. All right, over here. And just for those wondering, this did have a typo. This should also say increase, decrease, or no change. So we said nothing, and the reason it does not occur in the rate law. So on a test or something, you would write the SN1 reactions are independent of the nucleophile. You could also, I'd write the rate law as well and show that like it's not there. Okay, questions on this one? So what if we changed methanol to isopropyl alcohol?
static.
So, it's been a while since I've drawn it. I'm pretty sure isopropyl looks like this. So we know we have another alcohol. So what's going to happen to our rate if we switch this guy out for this guy? Nothing will happen to the rate.
Because still the nuclear.
Because this is the nucleophile. So it doesn't matter what we change our nucleophile to, it's independent of the rate law. It only depends on the substrate. Does that make sense? Okay, so I'm going to go ahead and erase this one. So we'll say nothing for this one.
What do you mean by substrate?
So the substrate is the reactant. Is the reactant,
The
but
reactant.
this thing, the one with the leaving group is called the substrate. So we'll say nothing.
Yes.
Because it's independent. You could also argue it would decrease. It depends why. If they're saying this is the product, and now you have a competing nucleophile where I would have this guy that was also able to bind to it. So it depends on your answer, but this is the official answer. But you would probably get credit if you argued that. So it all depends on, are you thinking about it, how it goes. All right. So if we removed the alkene, so that's saying we remove this double bond here, so I will draw part C right here. So if we were using this as the substrate instead, what do you think would happen to the rate then? So the rate would decrease, yes, because we just made our leaving group worse because we took away the resonance. Just like we said up here
Oh,
in this example. For that reason, we took away the resonance, and that would affect the type of substrate, and that does occur in our rate law. And since it's a worse leaving group now, it's going to be less likely to leave and thus slow down our rate. So I'm going to erase it, and we'll say decrease. And we'll say worse leaving group because the carbocation is not as stable. So now this one's a little bit tricky. And yet again, depends on your answer. So D. If we change the solvent to DMSO.
so it'll be aprotic.
Aprotic, exactly.
So it's going to slow down because SN1 prefers protic solvents.
Yes. And the reason it prefers protic solvent is it stabilizes the carbocation intermediate. Now dimethyl sulfoxide is like this, and it's one of the ones that generally promotes SN2. However, it is not in our rate law here, right? But it does affect the substrate because of its ability to leave due to its stabilizing. So you could argue nothing and probably get it right, depending on your professor, if you stated that it didn't occur in the rate law. However, the correct answer to this one is it will decrease the rate because it won't stabilize the carbocation intermediates as well. So we'll say decrease. If we changed it from tertiary to secondary, so we're now going to this. So what would that do to the
A
rate?
little bit slow because the
Exactly.
most preferred is the tertiary.
Exactly. So we affected our substrate again, and we made it a secondary resonance stabilized. We said tertiary resonance stabilized is better due to induction and hyperconjugation. So therefore, this would also decrease the rate. Chlorine to iodine. So we just changed our group here. Why is my marker? Oh, it's unhappy. So we have this now. What would that do to the rate?
So it's more down the column. So is it gonna increase because
Yes, it would increase the rate because iodine is a better leaving group, right? Because it's down the column. So this one would increase the reaction rate. Increase. So we affected our substrate, and our substrate occurs in the rate law, and we made it a better leaving group, so it's going to be more ready to leave. Just on a side note, iodine is a bigger atom than, say, chlorine. So I'm drawing like their atomic radii here. So if I have 1 minus charge on iodine and 1 minus charge on chlorine, I have more negative charge per area than I do in this one. So it's more distributed. They say it's more polarizable, the bigger ones. So that's why it's more stable. It's like putting a drop of food coloring in a cup or an Olympic swimming. So that's all for this. So I have some more examples here for the people that want to stay and work through some of them. So I'm going to go ahead and draw some.
I was asking if she did.
I don't know what it is. I haven't seen it yet.
I'm going to draw this one and work through it, and you can take pictures of it if you'd like. I'm going to draw one more, and then I'll hand it to you so I can work through this while you're taking pictures.
Oh, that's the practice quiz.
Oh, yeah, that's what I'm doing. Okay, so going through this first one here, it's saying it's SN2. KOMe is just methoxide again, potassium methoxide. So I can redraw this guy here as O minus. Yeah, CH3. Now it's SN2, so it's going to backside attack because we have a good leaving group here with a delta plus on this carbon, delta minus over here. So we're going to attack that. Form H. And we bonded to this carbon. Oh, I did too many. We bonded to this carbon here. So this carbon here. O. CH3. CH3. Okay. This one here. What type of reaction is this?
It's bromine, very specific. So it's gonna attach to a tertiary position.
And what is this thing here, HV?
Oh, HV is the light.
Yes, that's light. It can be written HV. They can also write light. So this one is going to brominate, and it's going to brominate the tertiary position, and that's because its brominations are very specific, and you form that intermediate of a carbocation, and carbocations are more stable on the tertiary position. Then the bromine radical is formed in the first step, attacks, pairs up with this guy, and you get your final product. This one. I'd like to go through one last one here before we end today, and that is going to be the reaction diagram for an E2 reaction. So,
Could you scroll back just?
yes.
Thank you.
Fine. This is the last thing, generally, other than Newman projections, that will probably be on the quiz. So let's do it. So for an E2 reaction, I'll make an example here. We'll have iodine, and we'll use NaOH. So we have a strong nuke, strong base, and we always take the strong base first, so this is OH minus. Na plus, we're going to form this sodium hydroxide. We have a good leaving group here, right? But E2 reactions are concerted, which means we don't form a carbocation intermediate. And remembering that's going to be important, because if you remember that, you know the diagram instantly, and you'll never get them confused. So no carbocation intermediates in elimination, because we're going to take this anti-coplanar hydrogen here, one of them. Since it's no stereochemistry shown, we don't have to worry about it. But we're going to take the one that leads to the most substituted Zaitsev product. The OH will attack the hydrogen. This bond will form here, and this will kick out the iodine. And we will get a tri-substituted alkene plus water, right? We formed OH with H plus H2O, but you don't have to draw this. So let's look at the energy diagram for this guy. So I have my reactant here, going up to a transition state. This is when the OH is attacking this. This is the transition state. And then immediately after this happens, we're at products. That should be a little bit. So we have our products down here. Yet again, this is energy, and this is reaction coordinate. So I'll denote that RC. So this is our transition state, and that's when this bond is collapsing, and when this bond is forming, and when this bond is leaving. So that's oh, this is not intermediate, this is supposed to be a double dagger. And we don't need to denote a 1 here, just because it's the only transition state that occurs. So that's our transition state. This is our reactants, which is this plus this, and this is our products here, which is this guy. Now, in this, we don't have 2 humps, right? So the rate limiting step is the first step, the transition state. And we can look here and see that it does depend on the base, right? Because the base's ability to attack affects it. But also, if there's no leaving group, it's not going to happen. So E2, elimination by molecular, is what the 2 means, is rate equals K substrate, so it depends on the substrate, times the base. So the concentration and the type of base also matters. So the stronger the base, the faster the reaction. The better the leaving group, the faster the reaction. So that's the rate law for this, and it's a concerted reaction, which means it's 1 step. So there's no real rate limiting step. The rate limiting step is the only step. So let's denote the delta, or the activation energy, the energy of activation, is between the reactant and the transition state, whatever the energy you have to put in to get over the mountain. So this is energy of activation. And then between the reaction and the product, here, this is delta H, the enthalpy of the reaction. Sometimes, yet again, also said a delta G. They show that sometimes. So in this reaction here, is this endothermic or exothermic? They like to ask that a lot too.
Is it exothermic?
Exothermic, yes. You're giving off energy in the form of heat. You started with, say, 100 joules, and you ended up at 50. So 50, if you were to do delta H, right? 50 minus 100, negative 50. So you lost 50, so you're giving off heat. So it's an exothermic reaction. So that would be exothermic. So they sometimes ask that. So that is the plot. This is the same plot for SN2. And then E1, like we showed earlier, I don't know if I still had it drawn. E1 proceeds through carbocation intermediate when you guys get there. So E1 and SN1 have the same plots. SN2 and E2 have the same plot. So if you're asked to draw an SN2 or E2, you show the same thing here. So any other last questions over any of the stuff we've gone over? All right, thank you guys for coming, and that concludes today's review.